Welcome to the last session of the conference. I'd like to bring up and first introduce the session's last speaker, Dr. Jessica Stauth. A quick bio introducing Jessica. Dr. Stauth is a managing director of research at Quantopian. Jess and her team are in charge of selecting the algorithms from the Quantopian community to allocate towards for our portfolio. Quantopian offers license agreements for algorithms that fit our investment strategy, and the licensing authors are paid based on the strategy's individual performance. Prior to joining Quantopian in August of 2013, Jess has worked as an equity quant analyst at the Starmine Corporation and as a director of quant product strategy for Thomson Reuters. She also holds a PhD from UC Berkeley in biophysics. So without further ado, here's Jessica Stauth.
So no one told me I was the last session, so actually I feel like this is great because it means after this, we're done. Which, not that it hasn't been a great conference, but only so many amazing talks and so much content you can stuff into your brain, so I hope you guys have an hour of content left to stuff into your brain, but stop me along the way with questions because I don't want you to all fall asleep in the back. So I'm going to talk about a little bit about how we have thought about this problem of selecting strategies from the crowd. Come on in. And then how we're thinking about it in the future. Oh, it's my fault. How's that? Sorry, I was all organized and then I didn't want to have a hot mic incident, so. Okay, so I'm going to talk about how we have tried to think about selecting strategies from the crowd, folks like you, and then how we're thinking about trying to improve it in the future. And quickly memorize that. This is not investment advice. Seems a little bit extensive. So I want to spend some time sort of explaining the problem statement and sort of how we've decided to try to approach this challenge, right? So the challenge is that, and if you went to Matt Rothman's talk, the challenge, right, is that we have access to a dangerous amount of code, a dangerous amount of data exhaust. So 175,000 people plus have written over 8 million strategies on Quantopian as of March. Now, the other part of the asterisk is what is a fully unique algorithm? That is actually one of the challenges that I'll talk about a little bit. And some fraction of those algorithms have predictive power in the market. I know that this is true because I have enough data on several strategies, a handful of strategies, that I know it's true, and I know it's true not in backtest and not in out of sample, but trading in the real, the real live market. So there's the existence proof, and a year ago when I gave this talk, I could not have said that. So that's something. So the question I want to sort of start to frame, and I want to emphasize that the way I talk about it today really is sort of starting to think about this as, could you frame this problem that we have as a machine learning problem, this problem of selecting the best algorithms from this really large data set? All right, so a little bit more about what this data set is and where it comes from. So we're not going to start, for the example purposes of this talk, with 8 million strategies. I'm going to start with about 55,000 unique, my little laser pointer is not super visible, so 55,000 unique user algorithms. So unique here is going to be defined as not a clone algorithm. We have an actual feature. If you're a Quantopian user, you know about it. There's a button you can press that clones someone's code. So we're going to say if you're a clone, just a full copy of another person's bit of code that they've shared on Quantopian, and you haven't made any modifications, you're not included in this study. And we had to do some, painful, detail-oriented work to find the, grandfather of all, children clones, and make sure that we always have the oldest copy of a unique piece of code created on the platform. And the other thing we're doing is, and this is also a pain, right, is saying, okay, well, so you may, I can't exactly guarantee that only clones are algorithms that are so closely related that maybe you've changed like a character or a line, or you've changed something that doesn't actually change the intent of the strategy. So we also have to go through and do some sort of clustering and say, if you're so highly correlated to another cohort of algorithms on the platform that I'd end up with big clumps of effectively the same thing, that's going to screw up my analysis, it's going to screw up my modeling. I have to get rid of you too. This process of uniquifying the individual algorithms is something that we are still continuously working on, and it's a huge pain. So just to sort of share some of the nuts and bolts. So how I think about this problem is you have code, but I'm not allowed to read the code. And even if I was allowed to read your code, I don't have a great idea of how, like, at scale, I would be able to read your code and make money from that. So find me afterwards if you do have an idea about that. Actually, I've had people suggest to me that you could inspect the code for, like, compactness and quality factors, and that some people think, like, that would actually be predictive, but we have not done that yet. And I think people would feel a little sensitive about me doing that. So I have code. The couple important things about that code is that all the code I'm going to look at was written 12 months ago, like on a calendar basis. So it's old code. Normally, you're not really that excited about old code, but I am excited about old code. It's time-stamped, version-controlled, encrypted at rest. So I have the ability to go into our database and say, time machine, back 12 months ago, give me every algorithm that somebody wrote on the Quantopian platform. I want, that code. Now, what am I going to do with that? I can't read it. I don't want to look at it. So what I'm going to do is I'm going to take all of that code and dump it into a big, wood chipper. It's my mental model of it. And I'm going to run simulations across all of that code. And the key here is I need apples to apples comparison. So if I want to say, I took all this code and I got a bunch of data exhaust from the simulations, I need to make sure that I'm asking effectively the same question of all of these different algorithms. So luckily, there's not that many different ways to run a simulation on the Quantopian platform. The parameters are start date, end date, and then a cost model and a capital base, which I didn't put the capital base here. So for this particular talk, I'm going to have a start date of June 2013, and I'm going to run the simulations through December of 2017. And I am going to include a cost model. So this cost model knows a bit about market impact, financing costs, and commissions, and it's sort of the best current model that we have to match our own trading that we do. Okay, so I run those simulations, and now what do I get out? So what I get out is a bunch of data. We sort of call this data exhaust internally. So what that data exhaust looks like is a returns object, a positions object, and a transactions object. So how much money did I make holding what stocks, and when and how did I trade them for every one of these 55,000 algorithms across this 4.5 year period. So now I have a bunch of backtest objects. That's still not so great. I'm like just one person. How am I going to look at all these backtest objects? How am I going to find out, again, what algorithms are good? So now what I'm going to do is, and here you can guess which of these three graphics I created myself using clip art and which were created by our professional graphic designer. So now we're going to extract features from this data exhaust. We're going to basically reduce this data set down from lots of big, complex, multidimensional time series into features that we think may represent those time series in a way that's interesting. So we're calling this thing the feature factory. And I'm accepting suggestions on better designs for the feature factory icon. For example, I think I don't feel like it's a really high carbon footprint feature factory, but this factory has a smokestack on it, so I'm still working on that. So this is sort of the flow of data through the process that I'm going to talk about. All right, so I thought it would be, this is a little hard to read, but I'll just step you through. Kind of useful to just sort of show you how sort of simple this data really is that's coming out of these simulations. So I've got returns data. I have it minutely, but for the purposes of this work, I downsample it to daily, so end of day. So that's really just going to look like, for each strategy, there's returns that I make every single day. So that's just a time series. I have a positions object I told you. So what is inside that? And this, again, I'm showing you an end of day positions object. So what's inside that? And I should say that this is using our public research infrastructure, and all the libraries that I'm using to do this analysis, or this part right here on this slide, are available to you on the Quantopian platform. So you can import our Pifolio lab, and I think this comes from an example that someone gave me from the lectures page. So this is stuff that you can do. You could run this type of analysis on your own, on the data exhaust that comes out of your own algorithm that you run a backtest on the Quantopian platform. So I get this positions object. So what's in here? What's in here is on December 2nd, here are some positions that I held, like unhelpfully with the SID instead of the ticker, and I'm a human and I'd rather not have to memorize that I think 24 is Apple or whatever. But anyway, it's fine. So here I have my SID, I have my last sale price, my cost basis, and my amount. So that's what positions that my algorithm held on this one particular day. So remember, I have 55,000 algorithms in 4.5 years, and so each algorithm held some arbitrary positions object on every given day. And then I have my transactions object, and that's like the most horrible, messy of all of them, because now I have like, oh, what did I buy? And this doesn't show you commission because I layer that in later. And we are using this market impact model, so it can take a parent order and break it up into children orders. But okay, this is the data that I have, right? Returns, positions, and transactions. So now, I told you though, like, I don't want to feed all of the returns, positions, and transactions into my model that decides what algorithms are good. I want to try to actually say, well, what are some features that I might be able to extract about that algorithm that might let me simplify the question of sort of categorizing it as good or not good. So we decided we would build this feature factory, and I have a couple of really smart data scientists that work with me, and I'm like, yeah, this is such a great idea, go build this feature factory. And they're like, yeah, it's awesome, we have like 82 unique and very interesting factors. And literally every time that I would go ask them, like, how's that feature factory going? They're like, yeah, we have like 436. We really think we've captured like every important factor. And I think they basically double how many features they've extracted like every time I ask, so I stopped asking. So you can come up with a lot of features, and I just picked a couple here to look at. So how many days you're invested, like what's your Sharpe ratio, what's your cost adjusted Sharpe ratio, what was your Sharpe ratio over the last year. So you can see that you can create a lot of features that can sort of almost start to revert their way back into being time series, and you have to be a little bit careful about that. But you also have other things like, what's the stability? What's the R squared of a linear fit to your cumulative log returns? We find that one to be like, I mean, it's really like so sad, but anyway, that one's really pretty predictive, I think. Like if your returns look like a straight line, you are kind of happy, whether you can really be sure you predict that. What's your beta, what's your alpha, and what's your information ratio, et cetera. So this is just a subset of the features that we extract. And then down the line, we have to decide, do we really want to include thinking about all these features when we try to decide what algorithms are good or not? All right. Oh, sad. Why doesn't that picture show up? Well, okay, you're not getting to see like a little bit of a cool picture, but I think you can see the numbers that are more important. So I mentioned that I want to sort of explain to you guys both how we have been thinking about picking algorithms to invest in and how we're going in the future. So I've sort of been explaining to you the way we're building this to be sort of more data science-ified. So here I'm showing you a little bit more of, well, what did we do to start with? So to start with, we said, we don't want to create a massive overfitting problem. We know that we're at severe risk of that, and we're trying to be really careful about not just looking through our whole data set and picking things that look good. We're going to try to come to this with prior knowledge. So this is sort of the way that we started out. And don't worry, I'll explain what some of these rows are. So we sort of started from more of like what I'm calling like an expert query approach. We said, hey, look, we have all this data about all these strategies, and so we should be able to sort of say there are rules and thresholds. So I think of it as there's some filters that look at what you want, and there's some filters that look at what you don't want. So for example, I want strategies that spend more than 80% of their days invested in the market. When you think about it, I'm not looking at a data set from a research team where I've told them, here are the parameters of the alpha signals I'd like you to develop, right? You have to be all invested all the time. You have to rank everything 1 to 100. It's not that. It's whatever random code 175,000 people wrote on the internet. And so some of them are doing things like on one day buying one stock, right? Many of them are doing things like being in Apple and then not being in Apple, and then being in Apple again and not being in Apple again. That's very popular. Or being in like, that's the most popular. That's also the most popular, when I look on like the Estimize platform, that's the most popular stock for people to rate as well. So everybody loves Apple. People can also do things like buying and trading instruments that I don't care about, right? So somewhere in here, there's this one, universe exposure to QTU with ETFs has to be greater than 90%. Right, so we have a Quantopian tradable universe. That's the universe of stocks at any given point in time that we're willing to trade in our investment vehicle. And we'll trade some ETFs, we won't trade other ETFs. For example, it's very controversial. I was like, I know you have a really great XIV VXX trading strategy, but I'm not going to allocate any capital to it. And people were like, you're so close-minded, until they're like, oh, this is kind of like not that bad of an idea. So we have to screen out stuff that's holding things we don't want. right? We are looking at things that have a certain frequency of turnover, so between 5% and 67%, let's say. So why do I care about that? If a strategy doesn't ever change its holdings, then I don't really know that it's making many independent decisions. So I kind of call that like the getting lucky portfolio. So there's no real good way, I don't think, to differentiate luck from skill. If you get like one chance, we all write down like our favorite portfolio and then we wait 12 years or whatever and we come back, like luck from skill is really hard. Whereas if I made you do that exercise every single day and I said, everybody's got to write down their favorite portfolio every single day, and you have to have, and you have to make different decisions, right? Then in 12 years, maybe we would possibly have some idea of who of us were lucky and who of us were skillful, although that's the hard problem. So what are these numbers over here? So INS means in sample. So the first N of these filters, and this is really the data set that I'm talking about, right? So the top set of these filters, I'm running this feature and I'm only looking at the time period that's in sample. So this algorithm was born or created 12 months ago. So I have like whatever it was, 3.5 years of data prior to that, and then I have a year of data that the author didn't look at. So these are metrics that I measure in sample, and just these last two, just to show you that if you said, well, okay, now I want to see how this has performed out of sample. So these last two measures, Sharpe ratio adjusted for leverage, and over 0.5. This does not seem unreasonable, right? This seems reasonable, like please have a Sharpe ratio of over 0.5. It's not that easy, and I'm sure a lot of you in this room who've actually tried to do this know it's not that easy. And then even more restrictive, although here it doesn't really show up in this data set, but I think that's because this is so hard already. I want your Sharpe ratio of your specific return. So I'm actually going to be so mean as to regress out all the returns you earned by picking a good sector or exposure to a good style factor. And I'm going to say I still want you to have a good Sharpe ratio on your alpha, your returns that have been having those factors residualized away. So one thing you can notice here that I'm not going to address too much directly in this talk is we're left with less than 5% of strategies at the end of this expert query that we then even sort of say we want to go look at those and consider whether we want to make an allocation to them. So one thing that, again, I don't think I cover much in this talk, but is something worth thinking about internally is I have to be so restrictive. I have to have like a really an expert query like this, because the way that Quantopian trades its portfolio today, every strategy really operates fully in isolation and has to be really well risk managed on its own. And that's a really extremely high bar to have. So we are thinking internally about what about the other 95% of code on the platform, and could we be more creative about thinking about ways to extract alpha and extract value from those strategies that haven't met sort of all of these expert criteria. All right, so this is the type of filtering that we had been doing. So could I turn this into a machine learning problem? I couldn't, I don't think. It turns out that's not really my background, but I know just enough about it to be dangerous, and I know enough about it to have hired a couple really good data scientists who are experts in machine learning. And so we've been working on this a bit, and I'm going to show you a little bit of first pass results. So a couple things that we learned really quickly were that if you want to feed this data set into a machine learning algorithm, you have to be careful about not overloading that machine learning algorithm with a ton of garbage. And this is like a recurring theme that I see, at least in this work, is there can be, and often is, just as much work that goes into what is sort of a bunch of crap that you need to screen out before you run your process, and how do you do that in a way that's not biased. So this kind of preview examples I'm going to show you, we've pre-screened down in ways that I'm not going to go that much into because we're still working on them, to a subset of about 7,000 of sort of the best prospects. And we're not going to use all of those features. I showed you, a dozen, and I told you we're coming up with, I think there's 600, although again, maybe the last time I asked there's 800. Anyway, we're going to use a subset of features to start off and sort of start with baby steps, so things like that we know are important, like turnover and risk exposures. We started off using just a very simple linear model. We've done a bit of looking at testing with support vector regression, and we're just using models that are available in sklearn. And I think for this set that I'm showing you, we're just looking at a 50-50 train and test set. So we take half of the algorithms. Remember, we sort of now, if we split our data set into a 50-50 train and test set, we sort of have 4 data sets. So we have our training data, where we have in-sample data that we and the author knew about that data, and we have out-of-sample data, right? And so we're going to use that training set and say the model is going to figure out what's the linear combination or whatever model combination of features from the in-sample data that predicts the out-of-sample data. That's our training. Now we take that model and we run it on the second half of the data, and we say, here's a cohort of 3,500 algorithms you've never seen before. What are you going to come up with? How good is it going to do? So this is looking at, on the test data set, what is the relationship, if any, between the out-of-sample Sharpe ratio that we predicted. So that's sort of like, in one sense, an important metric for us, right? We want to come up with, for every algorithm, a prediction. This bit of code represents an algorithm that, if I deploy it in the market, is going to deliver me a Sharpe ratio of what? And I've taken away the axes so you don't get either too distracted or depressed by where these, but you can probably guess where these center of masses come in. And then I have over here on the y-axis the actual out-of-sample Sharpe ratio. So again, early days and it's a small set, but we are indeed seeing some interesting hints that there are some predictive qualities in the features that we're looking at. But this also sort of shows you, yeah, this is a tough problem, right? So this is going to be a noisy thing that we're trying to predict. All right, so let's look through. I didn't go into too much detail about what features we included, but let's go through some of them. So what I'm going to show a couple slides just to give you a little bit of a taste of sort of the distribution of the data sets.
When you say, sorry to interrupt, but when you say predicted Sharpe ratio, is that just what it was in sample? Is that the prediction?
Okay, sorry, let me just go back to this. So the predicted out-of-sample Sharpe ratio, that is the prediction using the in-sample data of what we predicted the out-of-sample would be, and then the actual is the actual.
Okay. All right, so you're building a model of, it's not just what the Sharpe ratio was historically.
That's right, because we have found that to not be useful, unfortunately. And I feel like a lot of investors know that feeling. It's why we have to have these big disclaimers, right? Past performance is not predictive of future performance, except hopefully like a little bit, teeny bit it is, combined with a bunch of other information. And that's sort of like the challenge that we're set with. Okay, so here we're going to look at two different distributions. So in orange, I'm showing you the out-of-sample Sharpe ratio. So this is the feature that's computed on only the out-of-sample data. And at this point on, right, we're just looking at the testing data. So I told you we trained our model on half of our data set, and then we had fit our model. We now run it on the second half of the data set. So these are algorithms that our model hadn't seen before. So in orange shows you, the sad world of randomly selecting algorithms out of the database, investing capital in them, and like I did leave the axes on here. So here's your range of out-of-sample Sharpe ratios. So you can see, like, there's crazy stuff in here, right? There's like a long tail, like a negative 12.5 Sharpe ratio. You don't see those advertised very often. But on the other hand, you will see people talk about a positive 5 Sharpe ratio, and is that potentially is equally ludicrous. Although often whenever someone tells me they have like a Sharpe ratio of 5 or 10, I just ask them, like, are you doing HFT? What year is it? Are you doing HFT? And also, like, over what time period are you quoting me that Sharpe ratio? So I will have had people quote me Sharpe ratios, and it's like, that's over 3 months. Okay, well, fine. I can pick like a 3-month period, right, and show you like any crazy Sharpe ratio I want. So here we're looking at least, I think, a couple years of data. So that's orange, right? Orange is sad. Blue is still kind of sad, but it's starting to look a little bit better, right? So blue is the 150 best. So if I sort of come out with my my model's prediction, it's ranked every algorithm that I gave it from, I think this one's going to do the best, have the best Sharpe ratio. I think this one's going to do the worst. These are in picking the top 150 best. So you're starting to see like a little bit of a shift to the right, hopefully, that's the goal, and you're starting to see a little bit of a tighter distribution. So this is just another slice of the data that I showed you in the prior scatter plot. So something here maybe that's kind of sort of working. Yeah, I have this. So same thing, I told you we're also going to look at that specific Sharpe ratio. So that's just what if I regress out all of your returns that I can account for with, so we've built a risk model that looks at like 11 sectors and 5 styles. So same idea, a little more subtle, but I can start to see that the 150 best algorithms have a little more of a fat tail on the side that I'd like to see, although again, these numbers are crazy, so there's weird stuff in here. When I would start to look at this data and try to figure out like how can there be really crazy numbers in here, a lot of times it's because when institutional kind of quants are thinking about analyzing strategies, again, they're thinking in like really tightly controlled parameter spaces. And one of those is you're often saying, I'm going to be invested in it like 3,000 stocks, 1,500 long, 1,500 short. And so, okay, yeah, like it's very hard to get a totally ridiculous Sharpe ratio. Well, some of these strategies I've told you, I've not screened out here. I've screened out if you hold less than 10 positions. But you might hold 10 positions, and then you might have like 90% of your weight in one position. So there's some properties of these data sets that kind of end up looking like some kind of weird mixture of individual stock returns and behavior data, right? Because a strategy can hold, let's say not kind of one stock up to, a couple hundred stocks or a couple thousand stocks. So this looks like it's doing something a little bit that we like on the specific Sharpe ratio. So now we get to a couple of features where, like there, you know what's good, right? You want to be getting algorithms in your best cohort that have a better Sharpe ratio than randomly drawn. But now you can look at stuff like, what is the daily mean turnover of my 150 favorite strategies versus all the rest of the strategies? And here maybe you have like less of a prior, right? So you don't really know, I don't think. You might know some things you don't like and you don't think would do well. And so you can sort of see that a little bit. So we're thinking that strategies that have lower turnover are better. This is the way I'm going to sort of like flip the logic around. So if it's true that the 150 best strategies have a higher on average Sharpe ratio, you're saying, well, that's interesting. I've selected a cohort of strategies in blue that don't show as much turnover. So my blue distribution says, all these guys in yellow here that have 100% turnover, not very many of them made it into my 150 best, if that makes sense. Some of you look confused. I'm happy to like talk about my logic there. Yeah.
Depend on the cost model that you have?
Yes, it does. So if I took the cost model out, you would see there wouldn't be probably nearly so much penalty on these high turnover guys. That's exactly right. So hopefully, yes, basically yes. So that's why I wanted to stress this is with a cost model in there. If I made that cost model more and more and more penalizing, then it would sort of, it should show up.
So your cost model isn't a direct T-cost model, because otherwise turnover shouldn't matter, right? I mean, it should be endogenous into your alpha.
The cost model, what do you mean by isn't?
I mean, if I have a very high frequency, a very high turnover is only useful, right? Isn't it if you aren't measuring T-costs correctly? Because otherwise the T-costs should be taken for account in your net alpha.
They're not. In this, they're not. So like here we're not explicitly saying your alpha is residual of cost. We're looking at your return. So that Sharpe ratio knows nothing about the cost model. The specific Sharpe ratio also knows nothing about the cost model. Yeah. Yeah, I'll tell you. I attribute that to like probably some template that we published that has 100% turnover that many, many people cloned. So whenever you find things in our data set where there's like something that people are doing all the time, usually like we'll be like, that's interesting. I wonder why people decided to do that. Oh, because we basically forced them to, will often be the case. So that's what I think. Okay, so same thing. What is the distribution of the out of sample market risk taken on by the 150 strategies that this model liked the most versus the rest of them? And so basically you start to see, okay, we actually don't let, we're centralizing towards less market beta, which sort of makes sense, right? Because we're saying we're looking for a consistent good Sharpe ratio and a good specific Sharpe ratio. So we don't want either of those to look too bad. So the model can kind of learn, hey, if that's what you want, then you can't be invested in these strategies that take on a ton of market beta. And so I mentioned that stability metric, right, which is sort of this like embarrassing chartist style metric to say that you're looking at, right? If you're just going to like sort of fit a line through your log returns and say how close to 1 that is, that sounds kind of chartist to me. But it turns out that this model does kind of care about that. So, it's really saying that if you're very unstable, I don't prefer you. You're not likely to show up in my 150 favorites. Oh, it would be nice if this was more readable, but I'll explain it. All right, so those distributions are cool. Some people love thinking about the world in terms of distributions. Some people like thinking about the world in terms of like individual examples and anecdotes, so something for everyone. So what about like these specific algorithms that I'm selecting and saying are best versus the rest of them? So what do they look like? So these are some plots. I'll try to walk you through them, even though the legends are a little bit hard to read, but I think the colors are coming through at least enough. So these are plots generated by our Pifolio library. And these are, I think, all plots that are coming out of sort of the latest section that I'm not sure if it's in production or not. Maybe it is. Oh, sweet. That's amazing. Oh, of course it is. We never don't ship stuff to production. It's always immediately available. So this is after you've run your returns through our risk model, and you've got up here, what are my total returns? And then what are my specific returns? And so this particular strategy looks like, it does have some common factor exposures, and it's losing money based on them. So you might look at this algorithm and say, hey, buddy, if you run if you put an optimizer on this thing and you can limit your risk exposures, you might be able to improve your strategy a little bit. And down here, we're looking at what's the cumulative returns to sectors. So you're losing money in tech, and that's probably what that's showing up. And I won't go through all the rest of the plots, but basically, if I found a strategy like this and I looked at it and I went into like, where's the in sample, out of sample, I'd say, okay, this looks kind of not that bad. Some of them look, as I specifically say, super weird. So there's weird on Quantopian, and then there's super weird. So what's super weird about this is my specific returns. Okay, and again, I'm sure there are people out there that would show you a backtest and be like, yeah, this is my specific returns. Isn't that great? You're never going to take any common factor risk. You're just going to make money, and you're going to make more. Okay, that sounds great. So why would that look so weird? And remember, this is the data that we're feeding to our model. So we've asked this machine learning model to pick out who do you like and who do you want to invest capital in. I mean, it's not being that crazy to say, I like this one, right? It's just like making money like crazy, hand over fist, with no fail all the time. All right, well, upon inspection, the algorithm holds instruments that we don't take account that are not in our risk model, okay? And so I won't get into like all of why this is so sad, and we'll see if Renee is around, you can make her explain it to you later. But basically it means that you just sort of like taking all of your returns and pretending they're free money, but because of a bug. So this is a good example of, okay, so now that we know this, we can exclude these algos in that pre-selection step. So we are now really capable of evaluating this strategy, and we got to go and improve our process from there. But I like to include this because I feel like it's a good example of, you'll be working with data scientists and they're like, I totally understand all what is happening. I can look at all of the distributions. I can hold all the data in my mind. And you're like, no, pick one thing out and look at it. Is it sane looking, right? So we were sort of picking these out and looking at them. And I mean, this is probably the second or third one that we picked out of the stack. And it's like, clearly looks totally crazy and isn't a sensible bit of data to feed the model. So I find that to be super important. All right, so I want to sort of step back and say, talk about sort of why we think this, I've given you really just kind of like a taste of how we're thinking about turning this into kind of a data science problem. So, why do I think that that's a good direction for us to go, sort of extending past the expert query and into kind of data sciencing the problem? So one thing is we are making those predictions, right? So predictions can be used also as a pre-selection step to pass a more well-behaved cohort of models into the next step of our process, which is sort of a Bayesian statistical model trying to say, okay, for real now, how much alpha do we think is in these strategies? And that model gets really confused if you feed it a ton of crap. So there's sort of like a chaining argument of why I think this is interesting, but I don't have enough time to talk about that other part in the chain yet, so I'll leave it at that. The other thing is we can make predictions without out-of-sample data, right? We can't train and test if we don't have out-of-sample data, but we can take the model that we've fit and we can apply it to in-sample strategies. So if you write an algorithm on Quantopian today and you want me to tell you how good I think it is, I now have a model where I could feasibly try to give you some feedback about it, of how good I think it is. Whereas in the past we'd say, well, you have your in-sample data, so your strategy could be good because it looks good in backtests. I don't know if it's going to be good in the future. But here, at least, we're trying to model and make a prediction about out-of-sample data. So that's sort of what the next bullet is, kind of what I kind of backed into saying there is, this could be used as a real-time metric for algorithm quality over time. That could be interesting both to share out with the community, and it could be interesting to share with our product and marketing teams who look at us a little bit sideways when they say, we're trying to figure out, are we giving you better strategies? And I say, yeah, okay, like send me an email in 6 months and I'll look back at the strategies created today and see if they were any good. Okay, but all is not just rainbows and unicorns, of course. So what are some of the concerns? And then what are some of the next things that we have to do? So I mentioned a lot about the sort of uniqueness problem, and that this is like an ongoing thing that we have to work on. So that's one among several issues that results in the fact that our test and training set may still contain pretty similar algos. And if we don't do a good job of making sure that if we don't solve this correctly, we kind of have information leakage between our training and testing sets. And we'll think we've cross-validated our model, but it won't really be correctly cross-validated. We also have this issue of how to prevent learning things like the tech sector just goes up, or the tech sector just goes down, or the market just goes up, or the market just goes down. And also, we don't want to have selection bias through the use of out-of-sample data on training. And also, we're just getting started in terms of scratching the surface of, are we taking the right machine learning approach? Are there other models that might do a better job with our problem? All right, and I think I have a couple minutes for questions. These are robots, by the way, if you're not familiar with them. There's so many types of garbage. I feel like I'm like an expert on garbage. So like one type of garbage is like just we screwed something up. So the example I showed where if I look at specific returns, they appear to be an exponential function. That is basically like an artifact that our analysis has introduced into the data set. And so it is creating like a false signal that will then screw up the model that we're trying to apply it to. What are other types of garbage? So we try to weed out things where you're looking at like effectively like one stock. But like I said, it's like a lot harder than it would seem, because what's the right cutoff? So how many assets should you have to hold? And then what maximum percent in what asset? You can find cases where algorithms or strategies look good, but we then trace, one that Josh and I were looking at on the train the other day. You look and you say, oh, I have like a really weird discontinuity in my results. Oh yeah, that's because there was like a missed split adjustment in our database. And so there's like this step change discontinuity. So those are some examples, but unfortunately there's like a long tail of examples. And so what we have found is, and actually if you went to Joe's talk earlier today when he talks about like his computer game model, and that he realized like he got crazy ridiculous answers because he set all of his values to 0 except 1 because of a floating point issue. Like, so there's these kind of issues basically of like, you think you understand what you're passing into the model, and that one is a nice, very noticeable example of garbage that like screwed the entire thing, but then there can be subtle ones. So it turns out that kind of curating that input data set so that you're giving your model like what you think is sort of a fair, rational, and unbiased like picture of reality it is there. So I don't feel like I'm there. If I could even tell you, if I would be like allowed to even tell you, I don't feel like I'm really quite there. One that I'm saying has surprised me that was predictive was the stability feature. We did find, and I don't think I had figures on this, but we did find that the specific Sharpe ratio seems to be more predictive than the overall Sharpe ratio. So we've written down all these features, right? But this model here only used a small subset that we picked. So yes, we're very worried about just replacing our n-dimensional overfitting algo space problem with an n-dimensional overspace feature space problem. Not that I have not solved that. So what we tried to do is say, what's the simplest possible type of model we can start with, and what are sort of the fewest representative features that we think might be interesting, and then look at, okay, like how good do we think that is? Should we add something more? Is it orthogonal in some sense? And go from there. But yeah, I think that's just like another variation of the exact same problem. Like it mostly is empty, right? And so in some sense, what we're asking people to do is really, really hard. And the reason that you end up always talking about what you don't want is what you do want is simple, a thing that makes money. And so you're like, oh, that's cool, no problem. Just like sort on how much money you made. Problem is then there's all these failure modes of like, I can't invest in that. So one simple example would be, give me a bunch of strategies, sort on how much money they make, no other constraints, then I'll tell you, okay, yeah, that's cool. I looked at this one and it only trades, micro cap illiquid stocks, or it only trades ADRs I don't have access to. So I think very simply what you want is a thing where the equity curve is just a straight line of a slope you don't care that much about, because if it's a really straight line, you can just apply leverage that you want to it. But the problem is like that you want to know, is that straight line likely to continue into the future, and then can I have access to that return stream? So you then have to say, either I don't believe the straight line is going to continue that way because X, Y, Z, or I just don't have access to that. So it becomes like what you are looking for in some sense is very simple, like a thing that's making money, and then you say like, great, get all of those, but then I can't have them for all these reasons, and is there anything left over? And like I said, there are some, but not that many. So what I didn't talk about here is sort of the other research direction we're looking on is, okay, well, how could you compromise and not have such a extensive list of things you're unwilling to do? So, okay, I can't compromise on my investable universe, but maybe can't I pick a bunch of different signals which all do take some risk exposures, but which when added together in one big bucket, average out and can be left to be like sort of an alpha signal. And our current way we run our fund today, we can't really do that. So we're thinking about a way to try to take advantage of that, but it's more at a research stage. So it's sort of like trading constraints, and the way we've designed that first investment vehicle, we have to basically find like each strategy needs to be risk managed on its own and be like an alpha strategy, which is really hard. No, not perfectly straight, but yes, we have found ones that pass our criteria, and we've made allocations to N of them, and a small, like I said, a subset of them, I think it's smaller than what we need, have then indeed, had consistent performance over the first year that we've traded them in the market. So existence proof, yes, but it needs to be scaled, and that part is really, really hard from what we've seen. Yeah, I have 1 more minute, so do I have 1 more question? So I don't have in my mind like a good specific exact quantifiable answer, but once you say you can't take on any of these risk exposures, then we get pretty good diversity actually. So when you're really, really restrictive and you're looking for like pure alpha, and then you run just like now, in terms of then saying what is the like time series average pairwise correlation of all these things, it looks pretty good and pretty low. Now look, I think you do still get oh, here's, you do still probably have a commonality. I mean, I frankly don't think I certainly don't think there's 8 million different unique ideas on the platform, let's put it that way. And even when you get out your 150 best, are they 150 truly orthogonal ideas? Probably not. But in terms of like a simple thing like looking at the time series returns correlation, you can get it pretty low by just using like the risk model to pick alpha strategies. That's been my experience. And then the ones we've picked and traded, so like of all the failure modes you can have, we have not had like a crowding, like we have not had like, oh, in sample it looked like we had all uncorrelated alphas, and out of sample they've changed. That's actually been like one thing that's pretty persistent, and we've ended up with a cohort of, have very low average pairwise correlation in the strategies. So, okay, I think that's my last question. I'll be around afterwards, so please feel free to come introduce yourself and ask me more questions. And I think we'll share slides, but links are up here in references, so I'll leave that up.